Before we begin sketching the graphs of polynomial functions, we want to start off with a bit of a review about what polynomial functions are, as well as what a power function is, and how they work together to inform us about the end behavior of a function. So a polynomial function is a function of the form f of x equals a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power, plus on and on for however many terms we have until we get to a sub 1 x to the first power plus a sub 0. In this form, n refers to the degree of our polynomial. So whatever the largest exponent is constitutes the degree of our polynomial. A sub n x to the n, so the term with x being raised to that highest power, is the leading term. And our term a sub 0 is referred to as the constant term, meaning it's the term with no x variable, just a number isolated by itself. We do have a few specific additional statements related to these polynomials, or this general form. A sub n, that leading coefficient, can't be equal to 0. All the coefficients, a sub n minus 1, and so on, including that constant term, have to all be real numbers. Our value for n needs to be a non-negative integer. The domain of a polynomial function is always negative infinity to infinity. Its range may have restrictions, but the domain is always unlimited. And what we also want to make a point of identifying are some particular functions or a few examples of functions that would not be polynomials. So something like 1 over x, if we have a variable in the denominator, we're not dealing with a polynomial function. If we have x raised to a negative power, since that's again just the same thing as having an x in the denominator, or if we have x raised to some non-integer power, say something like x to the 2/3 power, those would be at least a few cases of examples where we're not dealing with a polynomial function. A power function is what's referred to as a monomial. So instead of a polynomial, a monomial, meaning a polynomial with just a single term, is something of the form f of x equals a times x to the n power. So we have a single coefficient, a single x being raised to a power, so only one term. Here a has to be some real number. And a can't be equal to 0. Our value for n has to be a positive integer. And so some examples of power functions would be something like 2x to the 3rd power, 0.01 x to the 8th power, anything where we have a polynomial function that consists of just a single term. For large values of x, whether we're considering large positive values or large negative values, a polynomial function will behave like a power function defined by its leading term. So something like f of x equals 3x squared plus 2x minus 10, we could say that as x gets very large, so as x approaches infinity, our function f of x will be behaving very similar to, or will be approaching the function 3x squared. So even though these two functions aren't equal to each other, as x gets sufficiently large, this first term increases much, much faster than any of the remaining terms. So if we just look at that leading term, that creates a power function which behaves very similar to the original function. And the same thing is true as x heads to very, very, very small numbers or very large negative numbers. In another example, if we consider g of x equal to 2x cubed plus 5/4 x to the 4th minus 1/5 x to the 5th, we could say that as x approaches infinity, or as x approaches negative infinity, so meaning plugging in incredibly large or incredibly small values, then g of x is going to be approaching, in this case, negative 1/5 x to the 5th. So this polynomial was written out of order. We still want to make sure we're identifying the term with the highest power, and that becomes our leading term. So this idea of understanding this power function that behaves similarly to our function for these extreme values is very helpful for determining the end behavior of a given function. So we have a few different cases that we can consider here. First, we'll consider f of x equals a times x to the n power. So we're dealing with a power function, and let's limit this exclusively to the cases where n is an even value. So we have x squared, x to the 4th, and so on. This graph will look generally something like this. Depending on that specific value for n, the rate of change of our function, the steepness will change. We'll get something relatively close to that picture. And a function like this will always have the behavior that as x approaches infinity, the function itself is also approaching infinity. So as our values for x get larger and larger and larger, so does our function value. As x approaches negative infinity, our function value is still approaching positive infinity. So as we consider smaller and smaller values, so as x gets larger and larger in the negative direction, our function still continues to increase. And that's what we consider to be the end behavior of our function. At those extremes, what's happening? In this case, our function is headed to positive infinity at both ends. If we have a case where f of x equals a times x to the n power, and consider n being odd, meaning we have x cubed, x to the 5th, or so on, we'll end up with a function that looks something like this. And in this case, as x approaches infinity, our function is going to be approaching positive infinity. But as x approaches negative infinity, then our function is going to be approaching negative infinity. So if we have an odd function, if we have x raised to an odd power, we're going to have n behaviors that are opposite of one another. So our function heading off to positive infinity in one direction, negative infinity in the other. We can also consider two similar cases where what we have is a negative coefficient out in front of our x factor. Again, if n is even, we're going to have that same sort of shape that we saw above, but now it's going to be reflected across the x-axis. meaning that as x approaches positive infinity, our function will be approaching a negative function value, or be approaching negative infinity. And as x approaches negative infinity, our function is headed towards negative infinity. In our last case, where we have a negative coefficient, times x to the nth power, and n is odd, we still have a graph that's headed in opposite directions at each end, but again, reflected, so that as x approaches positive infinity, f of x is going to be approaching negative infinity. And as x approaches negative infinity, our function value will be approaching positive infinity. So taking our n behavior and rewriting it as a power function defined by that leading term will allow us to match it up to one of these different types of n behaviors. Or specifically what we want to do is identify the leading term, identify the degree of that polynomial, so we know that it's either even or odd, and then identify the sign of that coefficient. And that will match us to one of these four cases, which will inform us about the n behavior of that graph.